right? You can hear me, right?
Yes.
Okay. So today we are going to look at shearing stress in thin wall. So this is the last part on shearing stress that you will see. Okay. And then we are going into a new chapter, pure bending, which is easier than shearing stress. I hope. I hope you'll find it easier. Okay. So let's look at shearing stress in thin wall. So in the thin wall section, okay, classification of structure are of structures are under number one is either a box beam. Okay, it's either we call it a box beam section, or we call it a white flange, or the second one is a white flange. So I've uploaded images on Avenue to Learn that you should download, okay, which will help you. So on the left hand side, what you see is what we classify as a box beam. Okay, so this is a box beam. As you can see, the structure looks like a box. And then the next one is you have a white flange beam section. Okay, so for both of the diagrams, what you see on both of them is V is coming from the top. Okay, and there's only one thing that is common in this diagram. Okay, this both diagram, there's one thing common. So what is this common thing is at the major web. So I call this a major web. This is also a major web. Okay, at the major web in this section, you realize that the arrow, right? The arrow is going from the vertical up direction, and then it's coming what? It's coming down. So that is for box beam. As you can see now, I'm highlighting it. And then for uh, white flange, also the same thing. You see this section over here. The shear flow, these arrows are your shear flow. Okay, by the way, I do apologize. These arrows are your shear flow. These are all your Q. Okay, these are all your shear flow. So you can see that the Q, the length of the Q. So I put note. Okay, I'm going to put note over here. Is that the length of the arrows okay, the length of the arrows is equivalent to the magnitude of the shear flow. Okay, so the longer the arrow, right, the higher the magnitude. So this is very different. So this is what? This is what we call under thin wall. So thin wall is very different from thick wall. Okay, what is the difference? So the difference is this. In thin wall, okay, in thin wall analysis, I'll write down here. Okay, so in thin wall analysis, right, the thickness is perpendicular to the shear flow. Okay, to the shear flow Q. So what do I mean by that? If you look at the box beam, this is the thickness. So this is the thickness for box beam. For thin wall, sorry. So this is the thickness, and then this is the thickness. Okay. And then over the other side, right, on the flange, this is the thickness. So this is what we call a flange, right? And this is what we also over here, this is what we call a flange. And then on the web, it's pretty straightforward, because on the web, whether it's thin or thick wall, this is our thickness. Okay, so this is for thin wall analysis. Whereas for thick wall analysis, okay, so I'm going to write a different one for thick wall analysis. Right, the thickness is perpendicular to the shear force V direction. Okay, so for thick wall, right, this is your thickness. So this is T. So this is for, I highlight that this is for thick wall. The confusing part is the flange. Okay, so for this case, at the flange, this is T, and this is for what? Thick wall. Whereas when you come to the web, it's the same, right? The web is the same, whether is it thin wall and thick wall. Okay, and then so this is the most important thing. What thickness you use? You use the wrong thickness, you're game over. Okay, so for thin wall analysis, the thickness is perpendicular to the shear flow. Okay, so that's number one. The next thing that I want you to look at is, let's look at the box beam. Okay, the box beam. Let's look at the box beam now. So for the box beam, point A is your start. Point E is where all the arrow will end up in. Okay, so you have your start and you have your end. So at point A, right, where you have the start, one arrow goes to the left and one arrow goes to the right. So this is your Q, and that side is also your Q. That's why you have the Q down here. Okay, one Q, the shear flow goes to the left and the shear flow goes to the right. Okay, so that's for box beam. For wide flange, okay, where is the start? Okay, so the start, you have two different start points. So you have a start here, you have the start here. So these are all your start. These are all your start. And then you have your end. You have two end points down here. So these are your end. Okay. So if we want to find at a particular point, we want to find the stresses on alpha at this point, we only need to consider this area. Okay, because you have two separate start points. Whereas for the box beam, if you want to find what is on alpha, right, the area you have to consider is this entire thing, because you have one start point and one arrow goes to the left and the other one arrow goes to the right. Okay, are we clear? So these are the rules that we have to comply. Okay, and then what other rules? Okay, so the other rules that you have to follow, let me find out where are my other rules. The other rules are these rules. Okay, these rules, you all should know this by heart now. Okay, so the other 5 rules are this. Sorry, I thought I copied already. So the other 5 rules. Copy. Come on, you cheeky sort.
Eugene, isn't there 4 rules?
Yeah, 4 rules. Okay, so these 4 rules still apply. Okay, and then on top of that, you have the box beam or the white flange. Are we clear? Okay, so these 4 rules, remember, all these rules, V and I are constant regardless of the point of analysis, still valid. Datum of analysis is at the center, still valid. Analysis will be carried out when Y variable is at its maximum, still valid. First moment of area cannot cross or intersect the centroid, still valid. That's the beauty of this rule. Fundamentally, this rule stands because this is derived from how we analyze the what? The shear force, okay, or the shear stress. And then if now for thin wall analysis, these are the add-on. So for box beam, as you can see, one arrow goes to the left, one arrow goes to the right because they have a common start point or the common what? End point. So that's why you have to consider the entire area over there if you want to find the stresses at point alpha. Okay, at point alpha. Whereas in the white flange, to find point alpha, you only need to consider that area. You don't need to consider what's on the left-hand side. This is because they have 2 different what? Start points for that reason. Okay. And then also be aware that the major web is the one that controlling the shear flow. Okay, so everything has to flow into the major web. Okay, and then out from the major web, the bottom. Question so far? Anyone?
Yes, sir.
Yes.
So for this analysis, are we only talking about these 2 type of beams, or are there going to be a different shape
No,
beam?
just this type, these 2 general type, box beam or white flange. Okay, only this guy, and these are the most common ones.
Yeah, looks like it. But I was just wondering if there's any other different
Yeah,
components.
you can have like L beams. L beams are also known as white flange, right?
Right, right.
Okay, all right. So I'm good. That's a good question. Let's look at. So rather than talking too much about theory, let's look at example number 1. Okay. I do apologize. Okay, can you all hear a noisy background at my end?
No.
No. Okay, it's okay there. This is because my neighbor has a like those rideable lawnmower, and he use it every once in a while. It drives me crazy. As long as you can't hear it, I'm fine.
I hear it now.
Oh, you do, right?
Yeah.
Yeah. Don't focus on it.
I could hear the trace of it like just 5 minutes ago, but now it's up.
Yeah.
Huh.
Yeah. My neighbor is a landscaper, and bloody hell, he drives a BMW X5. I only drive a bloody Mazda 3 for crying out loud. But anyway, and it's recorded. Right. So we are going to look at this section. I deliberately pick this problem. I repeat again, I deliberately pick this problem because this problem can be quite confusing. Okay, so knowing that a given vertical shear cause a maximum shearing stress of 10 ksi in a head-shaped extrusion shown, determine the corresponding stresses at point A and point B. So we know that tau max is equal to 10 times 10 to the power 3 psi, right? So the formula that we're going to apply is tau max, or tau, is equal to Vy over Izz Qz multiplied by T. Okay. So I'm going to call for my transformation. So this is Y, this is Z, rotation about X, and we have a Vy down here. Okay. So now with the rules that we know, right? Stress A, right?